Yes, thank you very much. Yeah, well, I feel very honored to have been invited to give the opening talk, and I'm not sure I am one of, there are many people, a lot of them in this very room, who have been very involved with the behavior of vectors, which kind of makes it a bit awkward to give a talk where I sort of want to talk detailed things to my colleagues who are active researchers in behavior, but I also want to sort of broaden out and kind of inspire people who haven't done much in their own careers necessarily with research-level behavior studies, just to show you all the different things that can still be done, and there's plenty more to do. Well, to start with, I thought I would just remind everybody that Alan Clemens wrote this book nearly, 18 years ago. It was the volume 2 on the sensory behavior and physiology of mosquitoes, which is like 700 pages and 2,000 references. And that was sometime 18 years ago. So since then, a lot has happened. And you'd have thought, well, why do we need to have a talk which is explaining why it's important to know about behavior? And the truth of the matter is behavior is very difficult to study. And every single species has its own very particular and specific behaviors and implications for disease transmission. So it takes a long time to find out what we need to know about all the species. But that's not the only reason. It's also difficult because you need to have some rather sophisticated tools. I've investigated the vision of mosquitoes, and their eyes are very small, and you have to have very special equipment to be able to really unpick how the visual system of a mosquito works. And so is the case for all the other sensory controlled behaviors. The other is that behavior evolves continuously. So every time we think we understand what's happening in a particular system, there can be new selective forces that change how those vectors behave. Say, for example, some species that we would have always considered to be rural village-type vectors have found ways to survive in urban areas and suddenly become a problem there. So behavior is not a fixed thing. It keeps changing over time. And as the human world evolves, so do the species that interact with it. But finally, perhaps one of the most important ones is that there is a difficulty for all people who do behavior across the board, for all the animals of the world, is that we have unconscious biases. We look at things and we think, oh, this might be so because that would make sense and that's very logical, and we project our own understanding of what we smell, what we see, what we hear onto our study animals. And sometimes it's very, very hard to lose those prejudices when you're studying behavior. And so I would say that there is a lot of behavior which is done slightly naively because there just isn't the depth of measurement of sensory systems and how they work, and about rigorous approaches to testing theories about behavior. And that's partly what I think my message today is, partly to inspire people who might think they're interested, but they think it's all been done. No, it hasn't been done. And to inspire you also. It may seem difficult, but it's incredibly rewarding. And so I would like to just present some of the things that I've worked on, or worked with people who've worked on, that did that for me, that got me really hooked on sensory control of behavior with respect to the practical outcome of vector-borne diseases. I always wanted to do research that had some sort of endpoint that was going to be of value. Let me see if I can do this. So many of you know the tse-tse story very well, but it just is, to my mind, such a model, a masterclass in how to go about finding a way to attract into traps, or to attract to control conditions where you're making the best use of the insect's own behavior, so that as long as it still has the behavior that it started with, and you present it with a certain kind of trap or a certain kind of control program that requires, that is predicated on host-seeking behavior or mating behavior, then you're always going to be able to trap them or kill them, but they might evolve other ways to evade your own particular type of trap. But in that case, it's probably evading human biting or evading the evading those sensory responses that used to make it a vector. So either way, the better you match your interventions to the actual behavior of those species, it's a win situation. So that the picture at the top shows the kind of the dedication that Glyn Vale had to being rigorous with his science. So he reckoned the first thing he wanted to know was, is there any olfactory, are there any odors that come off of cows that attract tse-tse to cows? And so the best thing to do is remove all of the other sensory inputs, like what a cow looks like, or what shape or size it is, or any warmth that the cow might be giving off. And he actually built a pit and buried the cow so that there was surface level no evidence that a cow was present. And then had this little channel that goes out to a fan on the right where he was pulling the odor of the cow out from the chamber underground. And here's where the cow, it sort of works. Anyway, in this picture you can see the cow's being, or calf really, is being brought down under the ground, shut the door, and then in the top right hand there's an electrocuting net with a dark target on it. So it is providing some kind of visual cue in this particular case, but you can see there's a little fan at the base of that square electrocuting grid, and that's a fan that's just blowing out the smell that's come from the cow. And what he found was that he thought he might need that black square to give them a focal point, otherwise they would just mill about. But thousands of tsetse fly landed on that square in the electrocuting grid, and then he took the square away so that there was very little visual target, and he said it was still as though I was standing there throwing handfuls of flies at the electric net. They were so completely obsessed with trying to find where the cow was at the opening to that pit. Well, people had argued before there was no point in worrying about odors because tsetse didn't use those. So it took something really robust and unquestionable to show and convince the world that odors did matter, and that took him about 10 years, I think, to convince everybody that that was true. So then he went on to the next cue that he thought might be important, and that was the visual appearance of a host. And so here we have a warthog on the left-hand side, which is the favored host for these savanna flies, and he got a stuffed warthog, so it looks exactly like a warthog, but it won't smell like a warthog. Okay, so he's taking away the smell factor by using this stuffed warthog. He expected that was going to be the most attractive one, but he wanted to simplify that because you don't want to make traps that are stuffed warthogs. That would be a kind of silly thing to do. And so he simplified it to this black drum that's, the orientation is very similar to the warthog, a cylinder parallel to the ground. But it's also an awkward thing with a stand, and it's sort of quite complicated to make. So he tried out a few box-shaped things to see how that would, what effect that would have. And there's not enough time. I wish I could tell you the whole tsetse story, but there was a very good scientist, Chris Green, who came and showed Glyn that tsetse fly, and he proved it electrophysiologically as well, have color vision, one of the few sort of flies that has true color vision, and said you must sort of mess around with these different colors. So at the end of the day, that box on the right-hand side is equivalent visually to the warthog at the other end. Now, that doesn't seem sensible to us. It doesn't look anything like a warthog to us, but that would be that unconscious bias. We would never think of going there if we were trying to replicate the natural host. But to a tsetse fly, that's just a perfect object, even though there isn't anything that exists like that in nature. But it just ticks off all of the sensory responses that take tsetse to a visual object. And so then here we have ultimately the target was also, those ones I showed you before ended up being traps that actually kept the flies. But this is one of the models of the famous tsetse targets where they land on black, but from a distance they're attracted by that blue color. So there's a step-by-step logical approach here. They come from a distance, circle around the blueness, and then they land on the black part, which is presumably they land on the underbelly of animals where it's shady and very, very dark as you can get. And so they like to land on the underbelly, and that's where they land. And these targets are just sprayed every 6 months with insecticide, And tse-tse biology is such that that crashes a population within 6 months. We have such a low reproductive rate. So he took it apart step by step and found things that work very, very well indeed. So I'll just take you back a few steps, because one of the things I feel is that people sometimes latch onto a particular behavior in isolation. So I'll just quickly sort of guide you through that thing. If we think about a tiny little sensor that's flying in space, which is what a flying insect is, there are a very specific way, areas in which they are going to have to use different sensory systems. So the range that smell can travel from a host is very, very far, meters. You can't pin it down exactly, but it's meters long. But it's only covering that little triangular area that I've drawn, because you can only smell something if you're downwind of it. So as soon as you fly down the slide or up the slide, or you go past that object, you can't smell anything because it's not there. The wind has to be carrying that odor to you. So actually, the area that odor works at is very, very large. It goes downwind, and it can go down. The sensory system of all these insects is so sensitive that it will pick up these molecules of odor way downwind, but then it has to find its way upwind. And the only way it can find its way upwind is by looking down at the ground and working out whether they're being drifted by the wind or they're going straight upwind. So in order to use this first primary sensory system, you have to have very good smelling and very good visual sensitivity to your relative motion to the ground. So that's what starts everything off. That's the biggest catchment area, is odor sense. But then once they get closer, the concentration gets higher, there's some indications that they're getting closer, then finally visual cues may kick in then. That warthog will be an object that stands out against its background. It moves, and it's of a different color than vegetation. And so within a much smaller range, but from all directions, upwind, downwind, not just necessarily downwind, they will see an object. But they still don't know if that's the thing they're going to. They need some extra information, which is, dare they land on it? Because it's a very risky thing to actually touch an object in case it's a predator or it's not what they actually want. It's a waste of time to land there. So there'll be very specific ones on a very, very small range of effect that actually gets them to land and touch the host and then bite. And those kind of sensory systems, very, very within that sort of box range of a host, will be what are their responses? What's a landing site? What are the cues that say, okay, stop flapping your wings and throw your feet out? What's going to make you do that, trigger that behavior? Correct convection currents will bring them down closer. And just the body heat, they have very, very sensitive thermal receptors. So all of these are very, very short-range ones. So if you're thinking about it, it's a whole progression of stages. And if you can't just go looking for something that mosquitoes like to land on, you've got to figure out how you're going to get them close enough to see it, to land on it. So you have to have all of these different things lined up. So what about mosquitoes? And this is a very famous picture that was drawn by McGilly's daughter, who I knew because I did my PhD with McGilly's in part. And so that's her lying in a hut. And this drawing is used very often. And it is ultimately the same idea, is that there are odors that emanate from a house. And then when an endophilic mosquito comes into the house, then picks up other cues. So it's kind of the same story across the board. But there's a huge difference here to the tse-tse story, because these are nocturnal species. And I think that part of that problem, that they're nocturnal species, held us back a very long time about thinking of different ways of doing trapping of mosquitoes, because we assumed they couldn't really see somebody, especially if they're lying in a hut in the dark at night. Vision isn't going to really come into it, is it? So that's kind of an unconscious bias not to bother with vision in nocturnal species. But what do we have? We have human landing catches, which are very accurate in the sense you are surveying, you're sampling the mosquitoes that land on a human being. So that's kind of exactly what you want to know. But it's still got problems. It's not standardized. One person might vary with another. That's been discussed very much, that human landing catches are perhaps not really ideal. And a light trap catch placed indoors next to a person under a bed net is another strong alternative, because that trap is actually catching mosquitoes that attempt to get to the person, give up. And my theory, but this has never been tested or actually researched and examined, my theory is that they go to the light trap because it's their escape response. They're now trying to just leave the hut because they can't get to the host. So it isn't actually attracting them as such. It's the little light is telling them this is the way out, and then they get sucked into the trap. So it's not a bad proxy for something like a surveillance tool. But both of these seem like they could have advanced further, especially after we have had Glenvale and Torr and Hargrove and all the people's understanding of tse-tse traps. You know, it just hasn't come into the tse-tse world. So I'm going to check my time, which I think is 2 minutes. So yes, it always happens. It's a very short time. But I won't go through the whole talk, but I'll be happy to talk to people separately if they want to know more about things. But so what I wanted to do is just to give a bit of a plug for mosquitoes and their sensory systems. So mosquitoes have these antennae, and these antennae are doing 3 major jobs. They're the most sensitive olfactory. They can pick up smells of hundreds of different odors that come from human breath, human bodies. These have been studied very, very well. They have those same antennae have receptors for sound, which is more sensitive than any other insect known. And they also, they have thermal receptors, humidity receptors, and so forth. So I've put this picture with just a mosquito at the tip of my finger, and the antenna is a little tip of that. And that's what this insect has got, such a highly developed sensory system. It's just unbelievable. Then the eyes are also very specialized, which I looked into, which means that they can absolutely see very well, better than any of us, to stagger home in the night in a dark African village. They can see well enough to navigate up an odor plume. And I think this wasn't fully appreciated before either. So I was just going to remind you of this range of attraction. So the picture holds, but for mosquitoes, it's slightly different because it's dark. They can't see very well. The air is calm, so that it's not quite as turbulent as it is in the day. So they've got quite a different strategy, but this underlying driving sort of system is still very similar. So these are the extraordinary eyes of mosquitoes, which I won't go into now, but they basically unevolved daytime eyes and reinvented a new kind of eye, which is very, very sensitive at night. And then I do quickly want to say, because I have run out of time, but Frances Hawkes came and joined me some years ago and started her PhD was on the behavior of mosquitoes under controlled conditions where we had a wind tunnel. I served as an odor bait, so that we sort of had a constant odor bait, and looked at all these questions. She found that as long as there was host odor present, mosquitoes respond to an object like that can that's in there. And that led her then to go on subsequently to a PhD now. She's continuing to work on this and has developed a trap which is based on all these principles, that there is odor coming from a person protected by that tent, so they're not being human baited, but they're human hosts. We're using whole odor until, I'm happy to encourage that we can change this to artificial odor, but for the moment using whole human odor, and it's ventilated here by this dark black object, which is surrounded with sticky paper, so when mosquitoes get the landing response, they land on it. And the magic sort of trick to make this whole thing come together was that she put water in that container that stayed at the temperature with insulation and so forth. It stayed at the body temperature. So it had all those 3 elements then. We had the odor, we had the visual cue, and then we had that thermal cue that told the mosquitoes to land. And please do look at the desk in the back, because we've brought some examples of zillions of mosquitoes that you get on this trap. And so I'll just finish. This is how you investigate it. That's what it looks like when you get these sticky papers. And this was the comparison that she did between this decoy trap, it's a sort of human-like trap, and the human landing catch. And you can just see from the heights of these at different seasons. The scales are different because at different seasons you get different size populations. But this decoy trap is just superior to a human landing catch no matter how you cut the cake, not just for Anopheles species, but Culex, Mansonia, even Aedes aegypti came to us when it was early in the evening. It was still out there. So I think this trap has real legs for sandflies, just using that principle of what is it that takes your vector from a sleeping state in its circadian low point to when it wakes up and it's picking up sensory cues. What are they? How can you replicate that and make a decoy that's going to work? And with that, I will stop. Thank you.